Question 16. This question is about magnesium, bromine, and magnesium bromide. A. The relative atomic mass is defined as the weighted mean mass compared with 1/12th mass of carbon-12. Explain what is meant by the term weighted mean mass. Well, so the mean mass is the mean or average mass of the relative abundance or abundances of the isotopes. So where all the isotopes that we have, we find the mean mass or the average mass of all those isotopes of that particular element. B1. Draw a dot and cross diagram for magnesium bromide. Show outer electron shells only. Well, for magnesium is in group 2. We're expecting magnesium to be losing 2 electrons, so you get the 2+, and those 2 electrons will be transferred to the bromine, and the bromine is in group 7. Now the 1 electron transferred to 1 bromine is that electron, and the second electron is transferred to another bromine, and this will be the dot and crosses diagram. Part 2. Calculate the total number of ions in 1.74 grams of magnesium bromide. Give your answer to 3 significant figures. First thing we do is to show the relative mass of the element, magnesium and bromine. This is the masses, and this is the number of protons, which is the number of electrons, because these are atoms. Atoms are neutral. And we need to work out the relative molecular mass for magnesium bromide, and the relative molecular mass will be equal to 184.1 grams per mole. Also, we need to work out that mole, number of mole in these 1.74 grams. Mole is mass over relative molecular mass, and we put 1.74 over 184.1, and that gives 0.0945 mole. How many ions are there? We got 3 moles of ions because we got 1 magnesium and 2 bromine. So that's 3 moles of ions. So we need to multiply that by 3 to give us the number of moles of ions. And now we need to find the number of ions, which means the number of ions will be equal to the number of moles of ion times Avogadro's number, and that will give 1.71 times 10 to the power 22 ions. So the answer we're looking for is 1.71 times 10 to the power 22 ions. Table 16.1c shows some physical property of magnesium bromine and magnesium bromide. Explain the physical properties shown in table 16.1 using your knowledge of structure and bonding. So for this part, the reason why we're given these values is to talk about the boiling point, conductivity, and for the substances. So that's what we're going to talk about. You can see the melting point for magnesium bromide is higher, and the highest is magnesium, which is metallic. So this is metallic bonding, and that's ionic bonding, and this one is a molecular structure. And so this is what we need to compare. For the magnesium structure, it's a giant lattice. It is metallic bonding with delocalized electrons. And if we look at the bromine structure, it's simpler molecular with induced dipole forces, London forces between the molecules. I'm talking about Br2 and another Br2 and another Br2 are linked together by induced dipole forces. Magnesium bromide is giant lattice of ionic bonding between cations and anions. Metallic and ionic bondings are stronger than the London forces, hence more energy required to break metallic or ionic compared to London forces. Magnesium metal conducts due to its delocalized electrons, which moves freely. Magnesium bromide in solid, ions cannot move, but in solution, ions can move, hence conduct. Bromine liquid does not conduct, as no mobile charge carriers are present in bromine. So you know about magnesium, when you do metallic bonding, it's going to be Mg2. So if we are doing metallic bonding, will be Mg2 plus and E minus, Mg2 plus, E minus, and that's what metallic bonding is, and this is what the electrons are, the delocalized electrons, so hence made it conduct. But the bromide, magnesium bromide, is we just done the structure, and that is Mg2 plus and 2Br minus. But when they are in molten state or liquid, they will conduct because you've got the charge carriers here. Bromine, Br2, has a structure with another Br2, and this bond here are the London forces, which is another Br2 here. So those are London forces, and those forces to break those bond here is weak compared to metallic or ionic bonding. This ionic bonding, that will be metallic bonding, and this will be London forces trying to break those bonds. Those are external forces, and these are internal, and the internal ones are more difficult than the external. The enthalpy change of hydration of bromide ions can be determined using the enthalpy changes in table 16.2. So we got the first ionization energy of magnesium, second ionization energy of magnesium, atomization of bromine, that means you turn it into gas from the bromine liquid to gas, atomization of magnesium, so you turn it down into gas as well, electron affinity of bromine, so you adding electron to bromine, formation of magnesium bromide, so you forming the ionic bonding, so lattice energy, the hydration of bromide ion surrounding the bromide ion with water, the hydration of magnesium ion, so you're surrounding the magnesium with water, solution of magnesium bromide. And these are the energy values for this. Part 1. An incomplete energy cycle based in table 16.2 is shown below. On the dotted line, add the species present, including state symbols. So we got this incomplete Haber cycle. So we're starting off with magnesium solid here plus bromine liquid. So that will be the first thing we start with here. So that should be magnesium solid plus bromine liquid. So from here to there is what we need. We need to populate this one, and you can see what's next between that and that. So after this is there. So which meant that we are making the magnesium gaseous ion to become magnesium gaseous ion 2. So we're losing another electron for magnesium from the outer orbital shell, and so we are expecting the magnesium 2 plus gaseous. We still have the bromine, so that will be 2Br gaseous, and the electron, so that will be now 2 electrons. 1 electron from here, and the second electron being lost to become 2 electrons. Part 2. Using your completed energy cycle in 16D1, calculate the enthalpy change of hydration of bromine ion. For the first ionization energy of magnesium, that will be here magnesium going on to magnesium ion. So this will be the gaseous becoming ion. So that will be 736. And the second ionization of magnesium is going to be going from the plus to the double plus, and that will be 1450. Then we have the atomization of bromine, and that will be, there's 2 of them, so you times it by 2, so this will be 224, because you got bromine here, which is 112, and there's 2 there, so you're forming the 2 bromine gaseous, and that has to be multiplied by 2, so 112 times 2, that's 224. The one going down here is the formation of magnesium bromide, and that formation, we can write that as the formation of magnesium bromide will be minus 525, and I put minus there because this is 0 here, so it's going down. So we got magnesium bromide, which is solid, and we're turning into aqueous, so we're adding water. So solution, we're making solution of magnesium bromide. So that would be minus 186. And this one here, this is magnesium solid becoming a gas. That's the atomization of magnesium. and that is 148. So we can write here 148. Now for what's left, I'm going from here to there. I'm adding electron to bromine, but this time there's 2 bromine, so I'm adding 2 electrons, 1 to each, and the electron affinity, meaning you're adding electron to bromine, so that's minus 3 to 5, and minus 3 to 5 I need to put there 3 to 5 times 2, that will be 650. And again, that's minus there because it's coming down. So from there to there, I'm changing the magnesium gas into magnesium aqueous. So I'm adding water. So that's hydration of magnesium, and that will be minus 1926. As you can see, that's hydration of magnesium ion. And the bottom one here, I'm going from, well, magnesium is already aqueous, so I'm hydrating 2 mole of bromide gas into bromide aqueous. So we can call that X. So let's just call that 2X. We need to find X because we need to find the entropy change of hydration of bromide ion. So we need to find the 2X. Now we need to calculate the value of 2X. So to do that, we got the 2 delta H hydration of bromine ion. Now is add all these together. So we're going to add all of them together. Don't worry about the sign. When we add them all together, we need to take away these ones on the right hand side. You add them all together, but they'll be minus because it's going down. So just add them all together, and we get 3 to 6 for the addition of all these. That's the blue one, 3 to 6, and the brown one, take away from the negative of the brown one, 2576. So that plus that is 2576, and the next thing we do is the difference is 693 divided by, because it's 2 of them, it's 2, so we divide it by 2, and that gave the hydration of bromide ion to be 346.5 kilojoules per mole, and that's how we calculate that. So the answer will be 346.5 kilojoules per mole. But it won't be positive because we can see that that's negative here. So the answer will be minus 346.5. And so we should put minus here. Part 3. Write the equation for the lattice entropy of magnesium bromide and calculate the lattice entropy of magnesium bromide. So the lattice equation will be the magnesium 2 plus, that's the gaseous, plus the 2 bromide gaseous as well. We give the magnesium Br bromide solid. To calculate the lattice entropy of magnesium bromide, we can see this is the gaseous of the metal and the non-metal, and we're going to form the solid. So what we want to calculate is from the solid bit here and the gaseous bit here. That's what we want to find. That would be the lattice entropy of magnesium bromide, which means I need to find that bit and that bit here, and then add it on to this bit here. So I need that and that. But we know the value from here to there is 693, and it's minus 693. And I know that the difference, the green bit here, will be 693 minus 186. And you can see what the 186 is this one here. So that's 186 here. That will give us 507. So now we see we want 507, so this is 507. And the pink bit here is minus 1926. So the lattice entropy of magnesium bromide will be minus 1926 minus 507, and that will be equal to minus 2433 kilojoule per mole. So that would be minus 2433 kilojoules per mole. As you can see, because it's all coming down, it's negative. So what we wanted was from the solid to the gaseous, because that's what the lattice entropy is.